Okay, good afternoon. Happy Friday. Happy Friday before Thanksgiving break. I know everybody's eager to get going. So, all right, let's get going. We have one more slide in the BJDC amplifier. So I want to work on the derivation, just show that. And then after that, we'll look at the MOSFET and the operation of a MOSFET device. All right, so first up is the derivation for a C amplifier. Now everybody has performed lab 8. Everybody's done with lab 8. So anybody remember what the approximate gain was for the CE amplifier? Absolutely. No one else remembers? RC and RE in terms of the resistor values. Okay. All right. So let's see. This amplifier uses a voltage divider bias, right? We will use the small signal analysis model or small signal model to analyze the circuit. In a small signal model, you're only looking at the AC portion of the analysis and a small, very small amplitude. DC sources are reduced to 0. That means they're all disconnected. Right? DC sources reduced to 0. So VCC at 12 volts connected to straightforward connected to ground. Output is taken at the collector. So this is VO. Input is given at the capacitor C1. So this is V in. Gain is denoted by A. Voltage gain AV is VO over V in. Okay, VO over V in. Also, in terms of impedance, means output impedance over the input impedance. Okay. So if the DC sources are reduced to 0, then the circuit looks like this. Actually, let's see. RE plus minus V in. Then you have VO and then RC. Okay, R1, R2 in parallel, RE, and then collector resistor. Okay. And then once we simplify the circuit, you can pick and choose a small signal model and replace the transistor BJT with a small signal equivalent. Okay. So we'll choose the hybrid pi model and I can redraw the circuit to look like this. Okay, we have nice dependent current source at the output, RO, output resistance, R pi, input side, and then see. We have V in here, V out here. We also have collector resistor, RC, and we have the base resistor,
The only thing
RB.
I got for myself at Dubai, was at the Burj Khalifa. I just got myself this little.
The reminder, if you're online, please mute yourself. Okay, so we have RB, we have R pi, and we have RO, output resistance, RE, emitter resistance, and RC. Okay. Keep in mind that RC, the bottom of RC right here was actually the top right here. So if that was the voltage, yes. Oh, hybrid pi model. We are using the hybrid pi model right here. This one. We could analyze the circuit with a different model too, but this one is easier. All right, so let's see. So as I was saying, the voltage across RC would be in this direction. Okay, so current's actually flowing in the opposite direction because current right here would actually be coming from the top like this. But because we use a small signal model, RC is now connected to ground on the other side. And so current is actually going up. IE is going down. RB, of course, is R1 in parallel with R2. IB, the base current, is flowing in there through R pi. And see, let's see what else. This current is coming down in R0. And that's about it. Oh, ZB is the impedance of the base looking into the terminals right here. Okay. And this could be GM VBE, or beta IB. Beta IB. Okay. All right. So, as with all things, we'll begin with KVL at the input side. So KVL at input loop. And I can write V in would be equal to the voltage drop across R pi plus the voltage drop across the emitter resistor. Therefore, V in is equal to IB times R pi plus IB times beta plus 1 times RE. IB is common, take it out, move it to the other side, and so you get V in over IB equals R pi plus beta plus 1 times RE. Okay, simply applying KVL. V in is the only voltage that's going in across the two terminals, and that is being split across two resistors, R pi and RE. So as straightforward as it gets when you apply KVL. Okay. Now, approximations. Beta plus 1 is approximately equal to beta. So approximations beta plus 1 is equal to beta, or approximately equal to beta. And then also R pi is going to be far smaller than beta plus 1 times RE. Okay. And so the approximate impedance as looking into the base can be written as beta times RE. Okay, beta times RE. Total input impedance Z in depends on the base resistor value. So input impedance is equal to RB parallel to ZB. Remember, our goal is to find VO over V in. To find that, we can find output impedance or input impedance. So we have done with 1/2 of the equation. We need to find the output impedance now. Okay. So ZO V in equal to 0. If V in is equal to 0, that means the base current IB is equal to 0. Therefore, beta times IB is also equal to 0. Therefore, output impedance ZO is RC in parallel with RE plus RO. Once again, RO is far smaller than RE, so it's negligible. Compared to RE. Therefore, CO is approximately equal to RC parallel RE. from here, the output, we know what VO is. VO is the voltage drop across RC, and the voltage drop across RC is in the opposite direction. And so can write VO is equal to minus VRC, the collector resistor voltage, is minus IC times RC. Therefore, VO is equal to minus beta IB times RC. IB we can find or not find, we can plug in from our previous steps. IB is V in over beta RE. Therefore, V out is minus beta RC times V in over beta RE. And finally, we have both. Therefore, V out over V in is minus RC over RE. That's how we arrive at that expression. Do the steps make sense? We got 30 minutes left. Questions? Lots of questions. Need some time for it to sink in. Yes. What part? ZB is the impedance as looking into the base terminal, from the base terminal, whereas the input impedance is RB parallel with ZB. Okay. All right, then let's turn our attention to MOSFETs. So MOSFETs are something you'll use in for 307 and going forward. So what exactly is a metal oxide semiconductor field effect transistor? What does it actually mean? Does anyone know what MOS stands for? Before you looked at this slide. Okay. So the name itself, I mean, FET, we already looked at. Field effect transistors. It's a transistor which is controlled by the applied external electric field, right? So it's field effects. Hence FET. The metal oxide semiconductor, MOS, stands for the sandwich layer across the gate terminal or on top of the gate terminal. And that's why it's metal oxide semiconductor. Okay. And then depending on the channel, whether it's P-type material or N-type material, sorry, not material, whether the channel is N-type or P-type, we have N-channel MOSFETs or P-channel MOSFETs. And so it's NMOS or PMOS transistors. NMOS are N-channel. PMOS are P-channel. And then when you have NMOS plus PMOS transistors on the same circuit, they complement each other. Complementary MOS or CMOS. That's where the term CMOS comes from. Okay. Yes. Yeah, it's there. In the notebook or chapter 5, JFET. First half was JFET, second half was MOSFETs. Yeah, FETs, part of FETs. So chapter 5. So the chapter numbers are corresponding to the ones that are there in the textbook. So FETs and MOSFETs are both in chapter 5. The only reason we did JFET before is because we have lab 6 before, and that's why we did JFET first. Okay, so as I was saying, it's a sandwich layer. You have a metal gate, and then you have a oxide layer right here. This oxide is the insulating material. Oxide is silicon dioxide. And then you have the semiconductor material, which is this substrate. So it gives us a MOS structure. Okay. Oftentimes, or in modern times, the metal is not an actual metal. It is heavily doped polysilicon. Okay. Heavily doped polysilicon. So polysilicon is simply silicon with multiple ordered segments, not single crystalline silicon, multiple orientations in the same structure. All right, so polysilicon, heavily doped, would have near metallic-like properties, and hence, which is easier to work with. Metals typically would be high temperature processes, and so in modern MOSFETs, we don't use metal much as heavily doped polysilicon. All right, so let's look at how and why these are very popular. Okay, MOS technology has been the standard de facto technology for pretty much all major microchips for the last several decades. Okay, one of the reasons is very low power consumption in the off state. So in a standby state, if you have like standard BJTs or diodes or intercomponents, resistors, for instance, it uses electrical energy or power at idle or at standby. MOSFETs, very little to no energy that's consumed. Okay, so to understand the basic operation of a MOSFET, we'll first look at what happens in that MOS structure. Okay, so the region of operation is the MOS structure, and that's where we will begin. All right, so metal oxide semiconductor. It goes to three possible states. They're listed right here: accumulation, depletion, and inversion. Okay, you have the metal gate on top. Okay, and then you have a P-type substrate in this case. This discussion holds true for both P-type as well as N-type. So you have a P-type substrate, And when you have a p-type substrate, actually, let's go back here a little. I just want to point out that was the metal gate, but I didn't point out the source and I didn't point out the drain. Okay, I'll talk a little bit more about the fabrication in the next slide after the next, the slide after the next. Okay. So in this MOS structure, what is happening is you have a semiconductor layer, which is right here, and you have the metal gate, which is at the top, and these two are separated by an insulating material, which is right here. The insulating material is made out of silicon dioxide, or simply known as oxide, hence MOS, right? So there is a certain threshold voltage that is based on the fabrication of the device. If the gate voltage, if there is a applied gate voltage that is far less than the designed threshold voltage, so at this point it is far less than VTN, meaning it is negative. And if you're applying a negative voltage, at that terminal, what happens to the electrons and holes in the substrate? If you apply a negative voltage anywhere, what happens to the electrons? Revoke your grades for like physics, send you back to take the prerequisites. Opposite charges attract, like charges repel. Fundamentals. So if you apply a negative voltage at the gate, electrons are attracted. Sorry, negative is applied, so holes are attracted, electrons are repelled. And so it builds a layer of holes or positive charges right underneath the gate structure. But there is an insulating material that separates the semiconductor from the metal. And so they accumulate right below the gate, but they cannot cross over. This is very important. Remember when I said low power consumption, right? There is no actual DC current that is flowing through that gate terminal. It's only voltage that is being applied, but there is no actual current that is flowing. So you apply a negative voltage from the top, it pulls all the electrons, or it forces all the electrons away and it pulls the holes to come up. So holes are accumulated right underneath that structure. Okay, holes are accumulated right underneath the structure. Now, if the voltage stays as it is, this is the off state or the standby state. Nothing else is happening. Okay, nothing else is happening. But now, let's say you slowly start to increase or make the gate voltage positive. So slightly positive. Okay. At one point, the holes that were accumulated are going to be pushed away because now the voltage is turning slightly positive. So that positive voltage is going to push away all of those accumulated holes. And what happens then is there is neither electrons nor holes underneath the gate structure. And it behaves akin to a depletion region. It is depleted of all mobile charges. Again, remember fundamentals. Depletion region means it is devoid or depleted of mobile or free carriers. It does not mean it's depleted of all charges because we still have the immobile ions in there. In a p-type material, you have the acceptor ions. In an n-type material, you have the donor ions or donor atoms, right? So those are immobile. They are not free to conduct. But the region is depleted of all free charge carriers, free as in free to move around and conduct electricity. So there are no free charge carriers there anymore. Okay. So first step was accumulation. You accumulated positive charge carriers in the p-type material. And that was just the region of accumulation or the state of accumulation. Then we turned the voltage slightly positive at a certain point, which is still slightly less than threshold voltage. That region underneath the gate is completely devoid of all free charge carriers. So again, there is no current flowing through that circuit. There are no charge carriers available, right? But now we increase the gate voltage far more positive and exceeding the threshold voltage. Now the exact opposite happens from accumulation. You have a strong field with positive charges at top of the gate. So it attracts electrons in that p-type region. And the electrons come up, again, shallow layer right underneath the gate, and it forms a layer of free charge carriers. So previously, in the standby state, we had positive charges, again, shallow region right underneath the gate. Then we went through depletion, and now those positive charges have been replaced with negative electrons or negatively charged electrons. So positive charges have been inverted to negative charges. Hence, this state is known as inversion. The gate voltage, VG, is the control voltage. So depending on how or what voltage we apply, we can control the internal mechanisms of this device. You apply a negative voltage, then it's positive charge carriers underneath. Nothing happens. There's no flow of current. And then you increasingly change VG to positive, and it inverts and it becomes negative. And that is the fundamental premise of operation of the MOSFET. Let's take a pause. Let me know if you have any questions regarding this topic. Any questions? "15 minutes. Did that make sense? Hopefully. Okay. All right. So accumulation, depletion, inversion. And let's see how we can use this for advantage. All right. Construction of an NMOS transistor. What's the first thing you notice? NMOS means what kind of channel is it? N channel. N channel. What is the substrate made out of? P-type. So N channel MOSFETs are made from P-type semiconductor material. And vice versa, of course, P-channel MOSFETs are made from N type of semiconductor material. This substrate is also known as the bulk or the body of the device. It is often noted with a uppercase B as a fourth terminal in the MOSFET. A fourth terminal in the MOSFET. Then inside this P-type substrate, we create two N-type regions. So this is an N-type region. This also is an N-type region. So there are two N-type regions separated by some distance. Obviously, all of these distances are exaggerated. And the width or the distance between the two N-type regions is the width of the channel between the two. Okay, is the width of the channel. A channel does not exist in this case. Okay. In a JFET, the channel already existed. It was a depletion mode device because we had to apply a voltage to turn the device off. We had to kill the channel in order to turn it off. This is known as an enhancement mode MOSFET because a channel must be created. It does not already exist. There are also depletion mode MOSFETs where a channel already exists from the manufacturer and we apply a voltage to turn it off. Okay. This one is the enhancement mode. Far more common. Okay, so again, this is a N-channel MOSFET. N-channel MOSFET is created from a P-type substrate. You have two N-type regions implanted on either side with some distance between the two. That distance is the length of that channel. The two N-type regions are labeled as the source and the drain. And the two regions are labeled as N plus, just to indicate that they are higher. They have a higher doping level than the P-type substrate. Okay, so a higher doping level than the P-type substrate. So far, so good. Okay, all right. So we have the source, we have the gate, and we have the drain. So the two N-type regions are the source and the drain. The gate is actually right here on top, and it overlaps. It overlaps the two regions. If it does not overlap, there will be a gap left between, and the channel would not connect. So the gate region must overlap both N-type regions. And then, of course, it's separated with an oxide layer or an insulating layer. Okay, so there is an overlap. And without the overlap, the channel would be broken. It would not exist from end to end. Is everyone clear on this? Okay. So, oh, and one more thing. Because this is a P-type and this is an N-type, it's basically a PN junction diode on both sides. Okay, on both sides is a PN junction diode. So if it's a PN junction diode and we do not want the current going directly between the body and the source and drain. So we keep the body and the source and drain reverse bias. Okay, so both of these diodes are kept reverse biased. So the body must be applied a negative voltage with respect to the source and the drain. Okay. All right, so here's the device operation. When VGS is far less than VTN, which was the first stage accumulation, we only have the two depletion regions right here, completely immobile, and then you have the positive charge carriers. Now you have positive charge carriers between the two N-type regions separated by the depletion region. So no channel exists between the two, right? The goal is to have current flowing between drain and the source. So at this point, if VG is far less than the threshold voltage VTN, and you apply a voltage between drain and the source, nothing is going to flow. There's no channel that exists, so there is no flow. You could apply as high a voltage as you want. You could probably end up blowing out the device, but nothing will happen. Okay. Now VGS is increased. It's only slightly more positive. So this is far less and negative. Slightly positive compared to the accumulation region. So now all the positive charges are forced down, And now you have created this junction of depletion region, and this depletion region right here merges with the two depletion regions that already existed in the fabrication. So now everything has merged together, right? This is the accumulation state. This is the depletion region, depletion state. And finally here, we have the inversion state. Okay. When you have a negative charge inside a circle, it is representing an immobile charge. Okay, so these charges are immobile. These are immobile ions. The acceptor, the immobile acceptor ions. Right? They accepted an electron, so they have one extra negative charge. It's a p-type material. So they are immobile. They are not free to conduct. So even though the depletion regions have connected from end to end, there's nothing there. But now the gate turns increasingly positive. So more positive, it attracts all the electrons up. So through the junction underneath the gate, and now it forms a shallow layer that connects both n-type regions together. And so now a channel is created between the two. Yes. Gate voltage is equal to, question being asked is what happens if gate voltage is equal to threshold voltage, depending on the functioning of the device. It can, in real life, it can never be exactly equal. So it could be on the verge of turning on, or it could be like on the verge of just turning off. So it'll be right on the border. The channel is just about to be created, maybe one or few millivolts here or there. If it's on this side, it might be off. If it's on this side, it'll be on. That's what would happen. Again, to put it in the most simplest of terms, you have two n-type regions on both sides. You have a p-type material underneath. I mean, inside the p-type material, you have two n-type regions. And you're applying a positive voltage at the top to pull all the electrons up. And those electrons, when they pull up, they would flow out of the gate, except there's an insulating material. So it stops right there, and it creates a shallow layer of n-type material. And that channel now connects both the n-type regions on either side. And that's why the overlap is important. If this did not exist, then there would be a break in the channel, and the channel would not connect to both ends. Does that make sense? And that's in short the operation of a MOSFET. For an NMOS transistor, you apply positive voltage to turn it on. PMOS is the exact opposite. You apply negative voltage to turn it on. Okay. So based on that, so now if you apply voltage between the drain and the source, current will start flowing because electrons will be able to flow from the drain to the source. Okay. You apply a voltage, VDS, similar to collector and the emitter of a transistor. You have current flowing between emitter and collector, and you have a base current that is controlling the flow of this current. So similar to this, we have current flowing between the drain and the source of a MOSFET, and you have the gate voltage that is controlling. The big difference is in a BJT, there is actual current that is flowing into the terminal. For a MOSFET, there is no actual current that's flowing in. So it's in a standby state, no power loss. Very negligible. That's the biggest advantage. Okay. How much time we got left? 4 minutes, man. That went by fast. Okay. Triode region. I'm going to breeze through this very quickly. So I already spoke about enhancement mode versus depletion mode MOSFET. This is enhancement mode, means the channel must be enhanced. Depletion mode, the channel already exists. We must apply a voltage to actually deplete it or shut the channel off. Okay, so these are enhancement mode MOSFETs. This is the triode region where you apply a voltage and you have linear response between the drain and the source. So if you plot a graph of ID versus VDS, this is what you would see. 1, 2, 3, 4. So varying values of the gate voltage. So all of these. Varying values of VGS. And then during this portion, all VDS and ID curves are linear. Hence the name triode region of characteristics. Okay, in this region, linear region or triode region, this behaves like a voltage control resistor. Okay, voltage control resistor. Now, at some point, similar to FETs, the channel will pinch off. Okay, the channel is going to pinch off. So when you keep increasing the voltage, right now the VDS is small. So your curve is going to keep increasing linearly. Then it pinches off. Okay, pinches off. So this is ID. This is VDS. And what you're doing is you're increasing voltage VDS. And this, of course, is for VGS far greater than 0. That's the maximum. Okay. When VGS is equal to 0, there is no channel. You would not get anything. So what happens is, similar to the FET, when you keep increasing VDS, this depletion region keeps on increasing. Because that depletion region keeps on increasing, at a certain point, the channel is going to start to shrink. So channel shrinks, and here channel pinches off. Channel pinches off. Okay. Similar to the FET, we would expect that if it's completely pinched off, then there would be no more no more current flow through it. But that's not actually what happens. What happens is that there's still a small amount of gap left in there. But electrons, there is a high voltage differential between the two ends. So electrons will drift through that gap. And once they drift through the gap, they're injected into this region right here, in a depletion region. And because of the very high positive drain source voltage, they get attracted by that electric field and are swept away out of the terminal. And so current then reaches a steady level. It behaves like a constant current source, almost flat lines. Okay. And so similar to an FET, you have a linear or triode region, channel reaches pinch off, then it saturates and behaves like a constant current source. So first it behaves like a voltage control resistor, then it behaves like a constant current source. Here, the electrons are actually pulled into the depletion region. Okay. All right. That was, well, it's already 4 o'clock, so we'll end here today. The last slide in this one is simply a summation of all the different MOS symbols. Okay. So for the most part, all material is covered. Okay, all I want to do is, not all I want to do. The more important point I want to do is I want to use the next, the final week to actually do practice on circuit analysis using BJTs and MOSFETs, which is something that we'll be doing a lot in 307. Okay, so we'll look at examples of BJT analysis, and then we'll do some theory and explanation and examples on MOSFETs. Okay, basic fundamentals. I might also, since we missed one lecture video this week, I'm going to say sometime this weekend, or at least before Wednesday, I want to record one lecture video and post it, so students can just view it anytime during the next 9 days. All right. So we'll end class here today. We'll meet again in 9-10 days on Monday. We'll have one final quiz, and then then just discussion and analysis problems. No, not on MOSFETs, BJTs. Yeah. Quiz question being asked is about the quiz. The quiz will be on BJTs. It won't be on MOSFETs. The MOSFETs thing is, it's a little weird. Officially, it's not kind of like part of 306, but fundamental knowledge is required before we move into 307 and 308. All right, questions? Go ahead. Oh, homework. Okay, sure. Let me stop recording here first.